Alright, are you ready? I think by now you kind of got the hang of it, right? Once you're done with sine and cos, it's quite straightforward with tan. So the part that makes sense for tan is the part between the asymptotes. Okay, like so. And again, by the way, you're probably getting sick of this, but 45-degree angle at the origin, roughly anyway. Okay. So what's the actual domain? Well, the asymptotes, they have equations of x equals pi on 2 and minus pi on 2 and positive pi on 2. Okay. So that's going to translate to horizontal asymptotes for the inverse. Okay, question. Is it increasing or decreasing? It's increasing, right? Just like this is increasing. Should have put the origin there. This is also going to be increasing. So off you go, 45 degrees, and there you go. Okay, no props. Now, by the way, because you will get asked to do this when you're graphing, right? Just like with tan x, this is tan x, but you know, in terms of appearance, it looks the same as 2 tan x, or 3 tan x, or 500 tan x, right? So therefore, just like you need a point for scale on here, and the standard is sort of like, what? Pi on 4, 1, right? Because tan of pi on 4, tan of 45 is 1. In the same way, you'd probably put, you know, if you just go over some distance, that's pi on 4 there. So that's halfway between 0 and pi on 2. So that makes this 1. Okay. Right, so that's tan inverse. So let's tidy it all up. So here's a table, okay? We did sine, then we did cos, and then we did tan. Okay. So domain. Now we're thinking about the inverses now, right? So remember when you had sine, right? That was this guy. Let's see. Okay. So domain is the horizontal values where it makes sense. So what's the domain of sine? Because what it came from, right? Remember, like in inverse, right? Domain and range came from the regular functions, range and domain, because we've swapped everything, right? Okay. So therefore, since the range of sine was minus 1 to 1, the domain of sine would be minus 1 to 1. Okay. Now, just to skip ahead, you know, cos inverse was the same guy basically, but sort of moved up and then turned around. Okay, so its domain is still the same. Okay, but range changes, doesn't it? We went from minus pi on 2 to pi on 2 here, right? But here we saw if you took that domain, it wouldn't work, right? Because that part of cos looks like this. It fails the horizontal line test, which is why we went from 0 to pi. So just to draw back to, you know, the first lesson when I said, you know, we don't really get inverse trig functions, so we use them, but we're like, I don't know, like they do the job, but I don't really understand them. Can you see what's going on here? This is the reason why the sine rule has an ambiguous case, but the cosine rule doesn't. Can you see? The sine rule. If you're using the sine rule in a triangle, like this, right? And suppose you had an obtuse angle there, okay? And you use the sine rule to find out what that angle was. Okay, and you know, suppose we knew it was obtuse. Okay, when you use sine inverse, when you use the sine rule, it can't tell you an obtuse angle. Why not?
Because it doesn't give you.
It's outside the domain. So what would it give you? If it can't give you the obtuse angle that it is, what would it give you? It gives you the equivalent acute angle. So you know, suppose this was 120, it would give you 30. Okay, and the reason for that is because when you think about sine of 120 is the same as sine 30. Okay, the values are the same, right? So sine has, the sine rule has an ambiguous case, but cosine doesn't. If it's an obtuse angle, it'll just tell you the obtuse angle because cos inverse can do that, right? Yeah.
So, did you say sine 120 is the same value as sine? Isn't it sine?
Yes, sorry, I meant 150. 150. I can't take supplements. Yeah. Okay, sorry, momentary freak out. Alright, but do you get what's going on there, right? The reason why the rules give you this, I always wonder, why isn't there an ambiguous case for cosine? And this is why, right? It's not arbitrary, there's a good reason for it. Okay, tan inverse, what's the domain? You can see it there. It just goes, right? Because for the original function tan, its range was all root values, right? So it swaps around. Now just a little thing to be careful about, right? The range of tan inverse is very similar to the range of sine inverse, but it's not quite, right? What's the difference? Yeah, you can't get these boundaries because they're asymptotes, right? So therefore, minus pi on 2 less than but not inclusive, and then pi on 2. Done. Yeah. Yeah, it should be. These should all be y actually. Sorry. I'm too used to writing x's and angles together. Good catch. Okay, make sense? Yeah. When I got taught inverse trig functions, this is where we started. I started with this table, and it's like memorize this. Okay, now let's use it. So I hope now that you've seen where it's all come from and why we restrict domains for inverse functions, it'll make sense to you and you'll remember it a little better. Okay. Now tomorrow, what we're going to do is work out what happens when you mix together inverse trig functions with the original function. So for instance, don't answer this if you think you know the answer, but just think about it. Are these two the same? If they are, why? If they're not, how are they different? Okay, things like that, and what happens when you actually put numbers in there? What happens when you mix them up? What if you take cos inverse of sine, or sine inverse of cos, and on and on and on? Okay.